Rationalizing a denominator. In this video, we're going to describe the difference between rational and irrational numbers, discuss a few reasons for rationalizing denominators, and then simplify expressions by rationalizing the denominator.
Real numbers means all the numbers on the number line. And the symbol is this fancy R. I want to talk about two main kinds of real numbers. The rational numbers are so called because of the word ratio. And the symbol is Q for quotient. It means all the numbers that can be expressed as a ratio of integers. And we can't have 0 in the denominator. Now, what kind of numbers are these? Well, any whole number will be able to be written as a ratio of the number to 1. 0 can be written as the ratio of 0 to 1. And a fraction like 9 over 13,273, or a negative number like negative 1/5, those are all rational numbers. Remember that fractions can be written as terminating or repeating decimals. But what about those decimals that don't terminate or repeat? Well, those are irrational numbers. They're all the real numbers that are not rational. Some examples are pi, square root of 2, cube root of 7. Those result in decimals that go on forever and don't repeat. If I have a radical in the denominator of a fraction, that's an irrational number in the denominator. If I rationalize the denominator, it means to change an irrational number into a rational number. Why? Well, Ask Dr. Math is a good place to find out why we do things in math. Here a student has written, what's wrong with having a radical in the denominator? And Dr. Math responds, one reason is to have a standard form. One reason is to help with simplifying. And one reason is old-fashioned. It was easier to divide a rational number into an irrational number by hand than vice versa. So that's a before calculators reason. Well, that's why we rationalize. What about how? 15 over the square root of 3 has an irrational denominator, square root of 3. Now, if I want to simplify a fraction, the way to do it is to multiply the numerator and denominator by the same thing. And if I multiply square root of 3 times another square root of 3, I'll get the square root of 3 squared, which simplifies to 3. Now 15 times the square root of 3 is over plane 3, and so 15 and 3 goes into 15 5 times. I end up with just 5 times the square root of 3, which is a much nicer version of the same expression. The trick was that since 3 is in a square root, I need one more copy of the square root of 3 to make a whole number. If I have a cube root in the denominator, I need 2 more copies because I need 3 copies of a cube root to make a whole number. So I'm multiplying the top and the bottom by 2 more copies of the cube root of 3. Well, in the denominator, cube root of 3 times cube root of 3 times cube root of 3 gives me 3. That's what I'm looking for. And in the numerator, I have 15, And 3 times 3 inside the cube root is 9. So I have 15 times the cube root of 9 over 3. I'm going to do that same simplification, and I get 5 times the cube root of 9. The trick was to make as many copies of the cube root as I need. Here's a fraction inside a root. We have the fourth root of 16 over a squared. First, let's separate it into two roots. That gives us the fourth root of 16 over the fourth root of a squared. Well, the fourth root of 16 is a perfect number. It's 2. 2 to the fourth power makes 16, so when I take the fourth root of 16, I get 2. But the fourth root of a squared isn't very easy to simplify. Well, if I had a to the fourth in the fourth root, that would be nice. So I'm going to multiply top and bottom here by another copy of the fourth root of a squared. I don't need 3 more copies because I already have 2 a's in the fourth root. I just need 2 more a's in the fourth root. Well, now I have 2 times the fourth root of a squared over the fourth root of a to the fourth, because a squared times a squared is a to the fourth. That gives me 2 times the fourth root of a squared over a. Now you might want to stop there, but the fourth root of a squared can be simplified if you think of that fourth root as a 1/4 power. I have 2 times the 1/4 power of a squared over a. And so that gives me 2 times a to the 1/2 power, because 2 times 1/4 is 2/4, or 1/2, over a, and that's 2 times the square root of a over a. Here's one that's slightly tougher. 4 is divided by the square root of 7 minus the square root of 3. This expression, square root of 7 minus square root of 3, cannot be simplified. Roots don't distribute over addition and subtraction. So I'm going to use a trick that's called multiplying by the conjugate. The conjugate is the same expression with the opposite operation. So since we had square root of 7 minus square root of 3, I'm going to write square root of 7 plus square root of 3. And I have to multiply by the same thing in the numerator and the denominator. Now in the numerator, I'm just going to hold off simplifying for a minute, but what I want to do is simplify the product of these two binomials, which, if you'll recall, FOIL goes like this. I have the first times the first, square root of 7 times square root of 7, which is just 7. I have the outer, which is this square root of 7 times the square root of 3. That's plus the square root of 21. Then I have minus the square root of 3 times the square root of 7. That's minus the square root of 21. And finally, minus the square root of 3 times the square root of 3 is minus 3. The middle terms, plus the square root of 21 minus the square root of 21, cancel out. And so what we have in the denominator is 7 minus 3. Well, if I simplify 7 minus 3, it's 4. And I have 4 times the square root of 7 plus the square root of 3 on the top, so the 4's cancel. And this simplifies to be the square root of 7 plus the square root of 3.